Welcome learners. In today's lecture, we are going to look into the parameters which we use to measure the performance of electrical signal in any given electric circuit. We will first look into the basic model of the flow of currents and the separation that creates a new element called potential difference or potential voltage. And these elements work on the principles of flow of charges. So first, we are going to look into that what is an electric charge. So you might have heard about the charge in your early education levels in physics courses, that charge is represented by unit coulomb. We write it as C as its unit. Normally we represent charge with a symbol of Q. So what is basically a charge? So charge is something that we associate with properties of matter. So charge is something which we associate with matter, and we know that matter is divided into four categories: solid, liquid, gases, and plasma. So all these elements consist the element charges, and the interaction or the motion of these charges basically generates something which we utilize to measure in our electric circuits, whether it is current or voltage. So when we talk about charges, we say that charges are bipolar, meaning their effects are related to the positive and negative charges. So we normally associate charge having a positive strength as proton, and if it has a negative strength, we call it as an electron. And obviously these charges have certain energy which they release or absorb. When it comes to protons, it basically radiates the energy. And if we talk about electron, it's such kind of a property of matter that it absorbs the energy. So basically these charges are radiating energy, or if we talk about in the domain of waves, these are generating waves or absorbing waves. So we say that these charges are bipolar in nature. Secondly, what happens when we analyze these charges and watch their behavior in any electric circuit? So here we can see in the image on to your left, you can see whenever these charges represented by these blue dots in any medium start to move, we are taking the conventional way or conventional flow of charges. So we can see the moment these charges start to flow from the positive side of the battery, they enter our load, in this case an electric bulb, and then the remaining charges move towards the negative side of the battery to complete the circuit. So we say that whenever the charges are in motion, it generates electricity, and we are going to talk about this generation of electric current in the next section. Similarly, if you look onto the image on your right, this is the atomic structure or atomic model of any atom. Let us say in this case it can be anything. So we know, or you know about this, that the atomic level, the center elements is called a nucleus, which consists of positive charges represented here by red and plus sign, protons, and then you have these neutrons. Then we have the outer orbit, or we call these as shells, which consist of electrons represented by the negative elements, and the outermost elements, whatever the count be, they are known as valence electrons. So these are valence electrons, and all these are better explained, if you remember, by the principle of Bohr's atomic model, where certain postulates are given by Bohr, which gives us the basic understanding of how an atomic structure is made up of and how the elements are moving around those objects. So what happens in this scenario is that whenever an electron moves from, let's say, point A, or where this point A is a certain orbit at the lower energy level, to point B, which is a higher orbit level, So it might gain energy. In this case, it gains energy. And if it moves from a higher orbit, let us say if it moves back from B to A, it is going to lose energy. So this concept then further analysis led us to believe that we have some kind of a difference of energy between them, which we call as voltage difference, or you might have heard about it as potential difference. So this difference generates what we called as a voltage. We are going to further look into this as well along with the current. So this is the basic property of charge which helps us to get the measurement tools for any electric circuit. The first one being the current, and the second one will be the voltage, as we saw here. So moving on, let us now first discuss the important measuring aspect, which is the current. So what is basically a current? So we normally define the analogy of current in terms of the flow of charges. So we say that whenever the charges are in motion, they generate an electric current in any medium. In this case, we consider it as a conducting wire. So current is mathematically represented as the rate of flow of charges. So we can say that if I want to know what is current, I can write it as rate of flow of charges. The analogy we normally give is, consider a water tube where water molecules are moving in a straight line. Similarly, consider those molecules being replaced by flow of charges. Let us say these are charges in any wire or conducting medium. So we can see that at the output, let's say if we are observing from this point, what is or how many charges are being received. So we can represent it by this mathematical expression, that current is the flow of charges per unit time, where Q is the charge and D is our time. But this definition is not accurate, because this definition is although telling us that the charges are moving, but we are not sure that at what instant of time the charge will be received, let's say at this point where we are observing. So this is our observation point. So in order to make it more readable or understandable, we introduce the concept of rate of flow of charges. So rate of flow is normally what is represented by this equation over here. So here we have introduced that there are certain amount of charges, but we have introduced the element of d by dt. D by dt basically tells us that if we are observing from this point, we say that at any instant of time, whenever the charge is received, we say that the current is generated. That's why we have used the term of d by dt, which is the small amount of charge at any given instant of time received to us, we consider it to be the current. The practical example could be, if I consider only this equation, that I would not be able to know that at how many seconds or how many hours the first charge is going to appear here. But if I consider the rate of flow of charge, I can say that any instance of time, whether it is millisecond, if we are lucky nanosecond, or if in even second the charge is received to us, we say the current has been generated or the output current is received. So that's why we always go with the mathematical expression of rate of flow of charges. Another important thing that we should know is how the current is flowing inside any element. So the image over here is basically giving us the comparison in the flow of current in terms of the conventional method and the current method. Or what is the conventional method is, normally we consider, or in most of our classical textbooks, we consider that the charges are flowing or they originate from the positive terminal and then they move towards the load or any element in between, and then it comes back and completes the circuit at the negative terminal. So this kind of flow is known as conventional flow of current. Conventional current flow. But on the other hand, as the science has progressed, we have come to this realization that actually it is the flow of electrons which directs the direction of current. So flow of electron is in the opposite direction of the conventional flow of current, which is originating from the negative terminal and then it goes to the or terminates at the positive terminal, and we call this as the electronic flow. So in our textbook, in classical textbooks, we always stick to the conventional flow of current which originates from the positive side, and concludes its path at the negative side. But for your information, the flow of electron will be in the opposite direction. So now that we have understood the basic governing definition of current, let us see what other things we need to know when we are working or we are finding the currents. So there are certain principles or basically rules that, or I can say important points for current. So that important point for example, the first point is that every current, or I can say each current, will have a value plus a direction. So we will come to discuss this point. The second point will be that for any given open circuit, current represented by I is always going to be 0 amperes. Ampere is the unit of current. And thirdly, if I want to find the flow of charges rather than the current in any medium, so I can find it as Q equals to integral of the current at that differential of time. So these are the 3 points that we need to keep in mind whenever we are discussing the current. So let us come to the first point and see what does it mean that current has magnitude and direction. So this is what it means. So whenever we are representing a current in any circuit, let's say if I have any circuit represented, this is the voltage source, this is the element, this is another element, and this is it. So this is resistor 1, this is resistor 2. So whenever this voltage source generates a current, we need to know that what is the direction of the current represented by this arrow and what is the value associated with this current. So it can be seen on these images as well that whenever we are discussing the flow of current, we have to respect the direction and the magnitude represented in figure A. It should be represented with an arrowhead and it should have a value. On the other hand, we always avoid this kind of representation that we only represent the direction and we don't know the magnitude. Similarly, in C, we also only represent the magnitude and we are not sure that where the current is flowing. So whenever we are dealing with current, we have to make sure that figure A is respected in the sense that the current should have any value. For example, it can have 5 ampere in this direction, it can have negative 5 ampere in the opposite direction. So but we always have to keep this in mind that the magnitude and the direction has to be represented. The second point being that whenever we have an open circuit, the current is always going to be equal to 0. What does it mean by open circuit? So let us say if I have a wire, any conducting medium, and it is represented by its terminals, terminal A and terminal B. So this kind of a wire, we technically call it as a short circuit. So this is a short circuit wire represented by SC. In this scenario, we know that the current can easily flow. So normally we write it as ideally the current is infinite amperes, which means the current can easily flow, there is no resistance. On the other hand, open circuit will be that if I take the same wire, but now I have a gap in between. So as you can see, this is the gap. Now the current cannot flow over here. We call this, if it has again the same terminals, we call this kind of a gap as open circuit represented by OC. Now the current cannot flow. This means the current is going to be 0 amps in case of open circuit. So this is what it means by open circuit. And finally, we can find the charges flowing through any conductor given any scenario. For example, let us say for the third point, I want to find, for the third point related to finding the charges, let's say I want to find the charges. So what is the charge, let's say inside a current carrying wire. So let us say I have been given this kind of a graph that shows the behavior or performance of this current. So the vertical axis contains the value of the current, let's say I1, horizontal axis is the time axis, and let's say I want to know that what are the charges. So what are the charges between these 2 points T1 and T2? So I am interested to find the amount of charges over here. So how can I find it? Very straightforward. We have the mathematical expression that charges are integral or integration of the current at that respective time. So we are interested only in the time domain of T1 to T2. So this is going to be I dt, and if you solve it, so it comes out to be T2 minus T1 I, and that's it. So this is the amount of charges passing through any current conducting wire. So these are basically the points that we should know whenever we are dealing with current. What else we should know? So let's talk about the double index notation. So double index notation basically gives us an idea that whether the current flowing is positive or negative. For example, if I have this figure A and figure B, and I say that I have a value of IAB equals to 5 amperes, then what does this IAB means? 5 amperes. So IAB is basically the terminals. Let's say this is A point, this is B point. So here it means that the current of 5 ampere magnitude is flowing from point A to point B. So this is what it means by IAB equals to 5 ampere. Similarly, if I write IAB equals to minus 5 ampere, then in this case the magnitude remains the same, but now the direction of current will be in the opposite direction. So this is now 5 ampere. I can also write IBA equals to minus 5 ampere. So IBA equals to minus 5 ampere. This means that the current is going from, so if this is my terminal A, this is my terminal B, the current should have been going from B to A, but the negative is saying that the current is going from A to B, and this is minus 5 amps. So these kinds of representations with subscripts BA is known as double index notation whenever we are representing the flow and magnitude of current in any electric circuit. Another thing that we will shortly see in the coming lectures is the representation of current, especially when we consider the current to act as a source. So we might have, or you might have heard about this term DC sources and AC sources. So although the generating or the element that generates this current is a voltage source, but we know that the output generated by the voltage source will be in the form of a current. So we normally represent the sources as DC and AC sources. What does it mean by DC? DC means that you have a constant or direct current. You can see the graphical representation of the behavior of this current, that we have time axis on the horizontal and the strength of the current on the vertical axis, and you can see whatever is the value produced by a direct current, let's say it is 7 amps, so it is going to be a constant value. There is going to be no shift in the signal. These kinds of currents are known as DC currents. On the other hand, we have another term which is known as AC currents or alternating currents. So alternating currents, as the name suggests, is something that is going to have a positive peak and a negative peak, then a positive peak, and so on. We normally call these as crests and troughs. We sometimes call them as positive peak and negative peaks or peak, and the relationship between these two are also known as peak to peak. So these are some of the terminologies to understand or analyze any given sinusoid signal. In this case, it is an alternating currents. So normally at our homes, we receive the voltages in our power sockets from 220 to 240 volts AC. These are the powers that are coming or generated from the grid station, and then they are transmitted through the high power transmission lines. They reach the substations, and then they are delivered to our homes. On the other hand, DC sources are those which are mostly used to power electronic devices like your cell phone batteries, your chargers, your tablets, computers. So these are basically dependent upon a constant DC source. So you might have a question that how we can convert this AC to DC. For example, for charging our cell phones. So there is a device called a rectifier which basically does this operation. So your charging devices or batteries basically consist of these rectifiers which converts the AC voltage into DC voltage. And for your information, keep in mind that although these sources are dangerous and not to be tampered with, but whenever you are doing lab experiments, you can experiment that maximum voltages, DC source voltage you can touch, which will just give you a tingling effect, is around 170 volts DC. So this is safe, you can touch it, but I don't advise it. On the other case, AC voltages are very dangerous because even a simple to 5 volts or more than that can give you a shock or tingling effect, or you can get paralyzed. So it's always safe not to directly touch the sources. Even if you are performing your lab experiments, you should have protective gear on. Wear those protective gears before you do the experiments. So this is an extra information for you. Okay, so now let us come to the next important measuring parameter, and which is basically a voltage source. So now what is a voltage source? So before we begin, you might have heard about this term, the potential difference. Potential difference, which we also relate to voltage difference. So we first understand the concept of potential difference, if you have not heard this term, which will make understanding of the voltage to be more easy. So potential difference is basically related to the potential energy of any object. For example, if I have, this is my ground, and I have a piece of ball lying on this. Somehow I provide it, or I lift this ball from this point A to, let's say, this point B. So this, it follows a certain height, it reaches point D. So now what we say is that this ball, which is at point B, has gained a certain energy which we call as potential energy, which depends upon the characteristics of the mass of the object, the gravity it has defined, and a certain height. So this is the mathematical expression of potential energy. And obviously, if now this ball is thrown from, let's say, point B to point C, if I try to then apply an additional energy, I say this potential energy converts into kinetic energy, which then formulates into half mv square. But anyhow, our focus is on this potential energy. So we can say, if we come back to point A and B, that this is the potential energy that the object has gained. Now consider that I have a certain charge of 1 coulomb lying on the ground. Let us call this as point B. And I want to now move this charge to point A. So now what will I do? I will provide it certain energy. Let's say that energy comes in the form of a voltage source or any external energy. Let us say I excite this in such a way that this charge is now moved from point B to point A. So this charge has gained certain amount of energy. So voltage is basically defined as the amount of energy needed to move a charge from point A to point B. And again, we are moving the small quantities, or we are interested in the small amount of work done to move a small amount of charge. So we differentiate, or again write the d omega by dq. So voltage is basically the small amount of energy done to move a charge from one point to the other point, where the one point is from point B at the rest level to a higher point, in this example point A. So this is how we define the voltage. So basically it is the amount of energy necessary to move a charge of 1 coulomb, let's say 1 coulomb, from point B to point A, or from a lower point to a higher point. We can, so this is how we define a voltage. Okay, so so if you read the definition, whenever positive and negative charges are separated, energy is expanded. Voltage is the energy per unit charge created by separation. This is the same thing that we have done. And why we are talking about the charges being separated. So in the beginning, we saw that the atomic model, let's say if this is one electron and one orbit, and this is the other orbit, let us say we have one electron over here, and we apply a certain amount of energy to move this electron from this orbit and bring it to this orbit. So this is basically how the charges are separated from their own orbit and they are moved to another orbit. So this is what it means by separation of energy or separation of charges. The most of the analogy or example that we give to understand the voltage generation is obviously the example of a water tank. So here you can see in the image that you had a water where you had this water tank and you filled this tank. You started filling it, and moment it started from here and accumulated, and then it reached to the maximum point. So what we say is that the water was at this point and it has gained certain height or gained certain potential energy and it has reached its maximum point. Now this is what we say the voltage has been, or the pressure has been built. Now in order for this pressure to flow, we can open this nozzle where all the energy stored in form of the voltage, potential energy, will start to flow. And we know that whenever electrons start to flow, they generate current. So this is a very traditional example which explains, or the water analogy which explains what is voltage, as it depends upon the pressure, and whenever the pressure or the electrons start to flow, they generate the output current. So again, certain points associated with voltage. So the points associated with voltage, some points, important points associated with voltage. Number one, voltage will have, so voltage is going to have a value plus a sign. We'll come to this point. Second point, voltage is only meaningful between 2 points. We'll understand this as well. And third point, if we have a short circuit, so previously we talked about open circuit in the current analysis. Whenever we have a short circuit, voltage is going to be 0 volts. So let us see the first point. So the first point is better represented by this voltage representation images. So we say that whenever we write a voltage, we represent it with certain value and give it a certain sign. So what does it mean? Let us say I have a voltage of -5 volts, and we have, for our own understanding, defined that it has a polarity of positive on the first terminal and negative on the second terminal. By the way, this kind of representation is known as terminal characteristics or terminal behavior of any device. So all these images A, B, C and D are the terminal representations of any device. What does it mean by terminal representation? We are going to look into this in the coming slides. But terminal behavior is that we don't know what is inside this box. We call this as a black box. We know that there is something and it is functional, but we are not interested. The only thing we are interested is the terminals shown here by point 1 and point 2. So for example, if I have a resistor, symbol is R, so this is its terminal 1 and this is its terminal 2. So terminals are basically needed to do the analysis of how the voltage is across appearing, how is the current flowing, and if you want to connect this to any other element, so we basically use the terminals. For example, I can connect this resistor to a capacitor with its own terminals. So this is what is the terminal behavior or terminal representation of device. So coming back to the first point, voltage will have any value and any sign. Now let us see how we can read those values and sign. So for example, let us focus on part A. We see that for our own understanding, we have designed a terminal device, terminal 1 and terminal 2, and we can see we have given the positive polarity to terminal 1 and negative polarity to terminal 2. So this is the sign of the voltage. And what is the value? The value in this case is -5. Now what this -5 is representing is that your terminal 2 is at a higher potential compared to terminal 1. So remember, we talked about voltage defining it as it is always the energy where we move something from a reference or a low point to a high point. So this is when we say that voltage is having a value of -5 volt, this means that the -5 is at a higher potential compared to the positive terminal, which is at the lower potential. And this also explains our second point, that voltage is only meaningful between 2 points, because the basic definition of voltage is we always move a charge from a reference level or a low level to a higher level. So which means that voltage is always going to exist between 2 points. So hopefully this clears the second point as well. Coming back to the first point and the remaining images, part B, C and D, let us compare A with C now. Again we can see that terminal 1 is having polarity of positive and terminal 2 is having a polarity of negative, but now the value of voltage is 5 volt, which means that terminal 1 is now at a higher potential, it has more energy, and terminal 2 is at low potential, or it is our reference point. Similarly, we can go to B and compare D with B. Now the polarities have been changed. Terminal 2 is at positive and 1 is at negative, but voltage is at 5 volts. Again, this means that terminal 2 is at a higher potential or has a higher energy compared to terminal 1, which has a low potential or is at a reference. Similarly, -5 volt means that terminal 1 is now at a higher potential in case of image D, and the other one is at a low potential. So this explains the voltage representation, and these things will be useful to us when we move to the circuit analysis of any given electric circuit model. And finally, coming to the third point, that short circuit will have 0 voltage. So by short circuit, we just saw previously that whenever we have any conducting medium, let's say a wire, and these are the terminals A and B. So short circuit means that ideally the current can flow through it without any problem, which means we can have an infinite amount of current ideally moving. So since the current can easily move, which means that this wire is not offering any resistance, which means resistance equals to 0. So how can voltage be 0 for a short circuit wire? It is going to be 0 based on the principle of Ohm's law. We are going to talk about Ohm's law shortly, but Ohm's law is represented by this famous mathematical equation, which basically shows the relationship between voltage and current, which is saying that voltage and current are directly related to each other, and the simplification comes out to be V equals to IR. So when we have a system where the resistance is 0, although the current is infinite, ultimately the voltage comes out to be 0 volts. So this means that whenever we have a short circuit scenario, let's say this wire, for a short circuit scenario, the voltage comes out to be 0 volts, and this is the thing we have to remember. On the other hand, if we have the open circuit wire, what happens then? So if we have an open circuit wire, let's say this one, so we know that in this case current is going to be 0 amps, but voltage is going to be appearing, because we will see later in the circuits that voltage is always in between 2 points. So let's say if this is a reference, so when we compare voltage, we are going to see its effects here, here, even here, and even here. So although there is a bridge, but the voltage is going to have certain value over here. So in short circuit case, voltage is going to exist in a short circuit case, voltage is going to be 0. In open circuit, voltage is going to exist and current is going to be 0 for the open circuit. Okay. Now we come to the next interesting elements, or something that we normally use in our daily life, and that is associated with voltage and current, and we call these terms as power and energy. So power and energy are normally derived from voltage and current. And why do we need to know about power and energy? Because normally when we talk about voltages and currents, so these are the measuring aspects of any electric circuit. So let's say voltage and current. If you remember the definition of electrical engineering, we said that electrical engineering talks about the generation of electric signals. So we generate electric signal, we then transmit it, and then we measure it. So this is what electric engineering is all about, talking about electrical signal in these three categories, A, B, and C. And voltage and current are basically used to measure the electric signals, and which means that if we have any electric circuit model, let's say this one, where we have a capacitor, resistor, and voltage source, we need to measure how much is the voltage source, how much current is flowing through this resistor, how much current is then appearing. So these are basically measured at any instance of time. But in normal day or daily life, we don't use them. Rather, we use the associated terms of power and energy, which are extracted from voltage and current. So we say that what is power? Power is the rate of expending or absorbing energy. And how did we reach to this conclusion? So we know that power is derived from the multiplication or of the voltage and current, and we know that voltage was the amount of energy or work done to move a charge from a lower point to a higher point, multiplied by current, which is the rate of flow of charges. So the power comes out to be certain amount of work done in a given amount of time, or a small amount of work done in a small amount of time, having the unit of watts. So this means that whenever we now talk about any kind of an element or a system, we talk about how much power that system is generating. So we are going to see that if we have any electrical circuit element, and if its output power is greater than 0 or less than 0, so we associate that if the element or circuit element is having a power greater than 0, that is basically absorbing the power. So this is another thing that we should remember: absorbing or consuming the power. And if we have a scenario where the power is less than 0, so we say in that case that element is basically supplying the power, or it is delivering the power. So we say that this is acting as a source because it is giving energy, and this scenario where power is greater than 0 is some kind of a load. Any electronic appliance like light, bulb, fan, that's we technically call these as loads. So this is where the power basically comes into play. Similarly, when we know about the power, energy is also associated with that. So energy can be figured out by just taking the time integral of power into d by dt. So these are the two terms that we normally use in our daily life whenever we are explaining any appliance's performance. The best example of these two can be, let us say, if you have a vehicle and you fill it up with fuel, and then you utilize that fuel to accelerate your vehicle. So we can say fuel is acting as an energy for the vehicle, and whenever that energy or fuel goes to the combustion engine, you basically accelerate, which means you are providing power to the system. So the more you accelerate, the more energy used. So this is an analogy where the energy and power are used side by side. Now let us talk about a very important concept in electrical circuits course, which is the passive sign convention. So now what is passive sign convention? So passive sign convention basically tells us that what is going to be the sign, what is going to be the sign of any mathematical equation used in circuit analysis. What is going to be the sign of any electrical model mathematical equation? What does it mean? We'll shortly look into this. So for example, if I have, say I have an equation of Ohm's law, V equals to I into R. Now passive sign convention basically is going to tell us that what is going to be the sign of this equation, whether it is going to be a positive IR or it is going to be a negative IR. So this is what the passive sign convention is going to tell us for any equation related to analyzing the electric circuit. Now before we begin talking about the images shown in front of you, we need to understand two things in order to understand the passive sign convention. Basically, we want to develop a standard method to understand the passive sign convention. So let us say if I have this terminal box or terminal analysis of any black box. So this is terminal 1, this is terminal 2, and I associate it with certain currents and voltages. So we know that voltage has a sign and a value, and a current has a direction and magnitude. So now let us say if I have this kind of a scenario, whenever, and let us now focus on the direction of the current. So whenever the current direction is such that it moves from positive terminal to the negative terminal, so it is moving from so you can see the current is entering into the positive terminal and it goes to the second terminal. So it enters the terminal number 1 and it goes to the terminal number 2. We call this kind of a situation as voltage drop. So whenever the current is moving from positive to negative terminals, we say we have a voltage drop. And whenever, let's say we have another scenario, this is terminal 1, this is terminal 2, this is now positive, this is negative. Now whenever the current is moving from terminal 2 to terminal 1, which is from negative to positive, we say this is a voltage rise. So now these are the standards that we are going to follow. Voltage drop means that the energy has been dropped. Voltage rise means that the system or the circuit has gained the extra energy. So this is what we are going to consider when using the passive sign convention. So this is the voltage drop and voltage rise. So now coming to passive sign convention to figure out whether any equation is going to have a plus or a negative sign. So whenever we see that the direction of current, so passive sign convention says that whenever the direction of current, what is the direction of current? This one, the arrow. Whenever the direction of current is equal to the or is equal or in line with voltage drop, we are going to use a positive sign. And similarly, if the direction of current, so let me use, if the direction of current is in line with the voltage rise, we are going to use the negative sign of that equation. So if the direction of current is in the voltage rise, we are going to use the negative sign. So these are the laws that we have to respect. Now let us look at the images and further understand what is happening. So let us look at figure A. We are finding the power associated with this voltage drop or the first terminal characteristics behavior. So we know that power is the voltage, the product of voltage into current. So P equals to V into I. Now we want to know through the passive sign convention whether it is a positive or a negative VI, this complete equation. So passive sign convention says that look at the polarities and the direction of the current. So here we can see that we have a positive polarity at terminal 1, negative polarity at terminal 2, and the current is moving in this direction, which is moving into positive terminal 1, and it is now taking the path from 1 to 2 and coming back over here. This means that it is in line with the voltage drop, which is from positive to negative. So whenever this happens, the sign will be a positive one as shown over here. Similarly, let's talk about figure B. Again, we want to find the power, which is a product of voltage into current, but we want to know what is going to be the sign. So we look at the direction of current and the polarities. Polarities remain the same as with A, but we see now the current is leaving the positive terminal, which means it is following the voltage rise. Whenever there is a voltage rise, we take the negative sign, or we take the negative sign convention. So this is what it means. Similarly, we can look at C and D, where now we have changed the polarities and we look at the direction of the current. So it is now falling from negative to positive. It's a voltage rise to opposite. So the sign will be a negative sign. And again, the current in D is leaving the terminal, which means it has entered from positive, which is showing a voltage drop. So we are using a positive sign over here. So this is how the passive sign convention works. Again, to summarize, we have to remember these rules for passive sign convention. First, we have to remember what is voltage drop and voltage rise. Then we follow these rules for the passive sign convention. That is, if the current is following the direction of the current is such that you see a voltage drop, use a positive sign, and if the direction of current is in the voltage rise, use the negative signs with any mathematical expression. Here we have given the example of power. We can also work with Ohm's law as discussed earlier. Okay, one more thing, that whenever we find the solution to this power, let's say this power comes out to be negative 40 watts and this comes out to be, let's say, negative 10 watts. So how can we say that this element is acting? So this element, since it's a negative value, we discussed that power is less than 0, so it is basically a source. And since this is a positive, which is a value greater than 0, so this is obviously a load. This is what we discussed in the previous slide, comparing sources with loads. To better understand this passive sign convention, let us have a look at an example. So here in this example, let us first focus on figure A. What is happening is that we have any arbitrary element over here and we want to know whether this is a source or it is a load. Similarly, we have a black box at the other end of the circuit and we want to know whether this is acting as a source or it is acting as a load. And what other information is we are having is that the polarities are plus and negative, and 2 volts is the magnitude. Current is moving in this direction from left to right with a value of 4 amps, and the black box over here is again having the value of 2 volts, negative and positive. So this is the same for both. Now let us say we want to figure out for the left side that what kind of element or load or source it is. So let us find the power for this side, for the left side. So we know that power is going to be V into I. We know that the voltage is 2 volts and the current is 4 amps. Okay, so it comes out to be 8 watts, but we don't know what is the sign. What is going to be the sign for this scenario? So let us look at the direction of current and how it is moving. We know if we look at this side, we know that current has left the negative terminal, which means it had entered from the positive terminal, right? So the current in this case has left the negative terminal, but it entered from the positive terminal. So we can say that this is going to be positive Vi. Again, I'll repeat, the current how is in this vicinity marked by the green is showing us that it has left the negative terminal, which means that previously it entered the positive terminal. So it is falling plus to negative, which is basically a voltage drop. So for the left side, we can see that it is plus 8 watts. The passive sign convention is giving us plus 8. This means that this side is basically a load because it is consuming energy. Now let us look at the right side and figure out what about this scenario. So again we find the power associated. So we can see that the power is equal to voltage into current, where voltage is 2 volts and current is 4 amps. And now we have taken the negative sign. Negative sign, why? Because now the current enters the negative and leaves from the positive. So here this is now acting as the source because the output will be negative 8 watt. And we can also confirm it because if you remember, we talked about the circuit theory conditions that the net charge of any circuit should be equal to 0. This means that if we want to find the total balanced power in this circuit, which means that the power absorbed plus power supplied should be the same or the difference should be 0. So we can say that the total power is that power absorbed is plus 8 watts and the power supplied is minus 8 watts. The output comes out to be 0 watt. This means that our system is balanced. So hopefully this example is clear. What about B? Let us look at image B and see what is happening over here. So again, let us find the power for this element and power for this. So I'm going to use this side. So for the left scenario, power is equal to voltage into current. We know that the voltage is 2 volts, current is minus 2 amperes. What about the passive sign convention? So we can see that the current is leaving the positive terminal, which means it entered the negative, which is a voltage rise. So it is going to be a negative 2 volts multiplied by minus 2 amps. So it is going to be plus 4 watts. So this means that the left side is acting as a load. So left side is acting as a load. What about the right side? So right side, again, power equals to V into I. Here the current is entering the positive terminal and leaving the negative terminal, which means it's a positive V into I. So it is going to be positive 2 volts multiplied by negative 2 amps. So it is going to be minus 4 watts. So this is acting as a source. So the right side is acting as a source, this one, and the left side is acting as a load. So hopefully this example further clears your understanding about passive sign convention. Okay, now let us talk about a few more things. What is a basic ideal element? So we previously saw these kinds of terminal behaviors of any ideal element. So ideal element is a two-terminal device. So let us put this into perspective. Let us say I have an ideal element called resistor. It has two terminals. This is terminal A, this is terminal B. So this is an ideal terminal device. It is going to have a certain voltage expression, let's say V, and a certain current flows in any direction. Okay, we call this as an ideal element because it cannot be subdivided to any other element. So that's why we call this an ideal element. We also classify these elements into two categories, like active elements and passive elements. Active elements are those that can generate energy. For example, you have a battery, that is an active element because it generates electricity or electric signals. Passive elements are those that consume the energy, but they don't generate energy. They basically provide or facilitate the circuit. And passive elements are normally RLC. You have resistor, inductor, and capacitor. So we call RLC as passive elements. So these are passive elements because they don't generate energy, but they support an electrical system. They allow the current to pass through it or voltage to appear across it. And these are the examples of active and passive elements. Finally, the lecture concludes by looking into a balancing power example, which we just saw that the absorbed power should be equal to the supplied power. So in this example, we want to figure out whether the power that has been applied or an absorbed is balanced or not. So we have been given a practical scenario of a home or a mansion, and we have made a equivalent model of this house. So this is a equivalent circuit model, not accurate, but it is something we created. So what is showing is that points A, B are acting as electrical sources to this home. C, D, and E are your wires or the electrical mediums which are carrying the currents, and F, G, and H are the appliances, might be televisions, lamps, hair dryers that are consuming. So now what we have been tasked is to use the data provided and figure out with the passive sign convention that what are the power associated with each element starting from A and ending to H. The respective values of voltages and currents are provided, and these are the things that we need to find. So basically we found the power associated with all the electrical elements starting from A, B, C, D, E, F till G using the passive sign convention. So let us take an example. We start with finding the power of unit A. Here we see that A is assigned positive terminal and a negative terminal with the value of VA. Current is assigned IA and it is moving from positive to negative. So the passive sign convention, if you want to find the power, is equal to plus V into I, where voltage is 120 taken from the table and the current is minus 10. So the output power is minus 1200 volts. Since it's a negative power less than 0, we know that this is the source, and this is what we have already mentioned in the previous slide, that A and B are the sources. Let us talk about B now. In B, we have current moving from the negative to the positive. It is a voltage rise, which means that the passive sign convention is going to be P equals to minus V into I. Here you can see it's a minus V into I. So we input the value of voltage and current from this table. Voltage is 120, current is 9 amps. It again comes out to be negative 1080 watts. Again, this is a source because its power is less than 0, and it checks what we have mentioned in this slide, that A and B are basically the electrical sources. So similarly, you find the powers for the remaining elements C, D, E, F and G, and you will get that whenever we have a positive sign with the power, this means that it is a load. In this case, F and H were the appliances, so we can confirm F and H are basically the appliances, and appliances basically are called consumers, or they are load to the system. So in this way, you find all the powers associated with this circuit model and the table provided using the passive sign convention. Now, once you have figured out all the power levels, you are asked to find whether the system is balanced or not. So in order to find the balanced system, we basically take the sum of the supplied power and the absorbed power, which means that all the negative elements are taken as one group. So here we get the maximum value of minus 220, minus 2290 watts, and the absorbed power comes out to be 2270 watts. So the total power is showing a difference of minus 20 watts. The ideal case should be that the total power or the balanced power, which is the difference of the supplied or the absorbed power, should be equal to 0 watts. When it is 0 watt, it means that the system is balanced, or distribution of electric signal is balanced. But since we are having a negative 20 watts, this means that the system is not balanced. So a good thing about the electric circuit is whenever we do an analysis, we can figure out where the problem is. There are some scientific methods associated to figure out the problem, but as a start, we can see that where the problem lies. If we go back to the table and find a simpler way to find that what is the problem, what we can do is we can divide the balanced value or the difference in balanced value, let's say minus 20 watt divided by 2, we get a value of minus 10 watt. Now we go back to the table and figure out that which element was giving the power of 10 watts, and we saw that element D was originally having a value of minus 10 watt. So if we go back to the table, here the voltage was 10, but the value of D, this came out to be minus 10. So this was the problem, that it shouldn't have been minus 10 watts, rather than it should have been a positive 10 value. So instead of taking minus 10 over here as P of D, you can see here, if we change it to plus 10, then this value comes out to be 2270 watts in a negative. Once we have this value, we put it in the supplied value of here, then the output will be 0 watts. So this means that circuit analysis gives us the possibility to analyze which elements are consuming or losing power, and we can rectify that error. So this is the simplest approach of doing the circuit analysis. In the coming lectures, we are going to mathematically see which methods can be used to figure out which elements in any circuit model are not working correctly or have been given the wrong values. So this concludes the first chapter from our Nilsson and Riedel book. Thank you very much.